Hey guys, today we're going to be doing some kinematics. So this is unit 1.1. We're going to be discussing position, acceleration, and velocity, their relations, frames of reference for different kinematics problems, gravity, what is gravity, how does it act on objects, and basic kinematics formulas you need to have grounded down before your AP. Alright, let's get into it. Okay. First, what is position? Position is your location relative to a certain point. So let's say you start at your house. Okay, this is a little house. This is where you live, and you walk 15 meters in this direction. Then you traveled a distance of 15 meters, and your position relative to where you started, or from the place you started at, is 15 meters east. And these are vector quantities. By now, you should know what vectors are. Vectors are basically a, a magnitude or a number, like 15, in a certain direction, which is east, in this case. So, basically, now let's look at frames of reference. So, velocity. What is velocity? Velocity is your distance traveled divided by how long it took you. So in this case, you traveled 15 meters east from your house. Let's say it took you 3 minutes to travel this distance. So velocity is equal to distance over time. Distance traveled is 15 meters divided by the time of 3 minutes is equal to 5 meters per minute. Cool. Now, what is acceleration? Well, as we saw, velocity is how much your distance changed over a certain interval. Just like that, acceleration is how much your velocity changed over a certain interval of time. So, let's say you started off let's say you started off with a velocity from your house of 5 meters per minute, meaning when you left your house, you're walking at a speed of, if you walk for a minute, you would travel 5 meters. But after about 10 minutes, you were walking at a speed of 10 meters per minute. Or if you kept moving at the speed you ended at for a minute, you would have traveled 10 meters. Well, how would you find your total acceleration over this period? Well, you would take your acceleration formula, which is change in velocity over change in time, or v over t. Your initial velocity was 10, your final velocity was 10 meters per second or per minute. Subtract your initial velocity, which was 5 meters per minute, divided by the total time it took you to accelerate this amount. So the trip was 3 minutes long, as we discussed. Cool. So now you ended, the time interval started at 3 minutes, and obviously it ended at 0 because time starts at 0. So your acceleration over this interval was 5 over 3 meters per minute or meters per minute squared. 5 over 3 meters per minute squared. Cool. So these are acceleration, velocity, and position. How does frame of reference tie into this? Cool. Let me ask you a simple question. Are you moving right now? Your answer would be, well, if you're sitting or laying down or standing, you'd probably no. Depends on your perspective. How the Earth is spinning at around 500 miles per hour. So, someone who is, let's say, on the International Space Station, if they had like a really good telescope and looked at you, you would look like you're traveling at 500 miles per hour. Someone outside our solar system would think maybe you're moving at 1,000 miles per hour. relative to a different position in our solar system. And some maybe we're moving at 1,000,000 miles per hour, which might exceed the speed of gravity. I don't know. And basically, the point I'm trying to make here is that depending on what perspective you're looking at a problem, your your speed, acceleration, and position may vary. This tool of knowing how different frames of reference tie into different speeds is vital to solving certain kinematics problems. Let's take the example of someone sitting in a car. So there's a guy, and he's sitting in his car, and his car is moving at a velocity of 50 meters per second, which is really fast. Okay? Now, let's say this person jumps up at a speed of, he jumps up at a speed of 10 meters per second. If I ask you, how much did this guy, what was his total displacement? Or how much distance did this guy cover over his jumping period? Well, depends on where you are. A viewer who's not inside the car would see this person travel or on a trajectory like this, where he went up 10 meters per second, but he's also traveling right at 50 meters per second. However, if I was in the car with you and I saw you jump, I would only see your displacement or your velocity 10 meters per second upward because I'm in the car with you traveling at 50 meters per second. Rewatch this video or rewatch a section of this video to really understand this concept of how if your frame of reference varies, then your perception of a problem can change as well. Another example is a conveyor belt. Let's say you're on a conveyor belt and it's moving in this direction. If you were standing on this and you bounced a ball up and down, up and down, up and down, up and down. Well, the ball, when it touches the conveyor belt, let me just zoom in a bit. When the ball touches the conveyor belt, because the conveyor belt is moving this side moving to the right with a certain velocity, the ball will also move at that velocity when it touches the conveyor belt. So it would go not only have a velocity downward when the person pushes the ball down, but the ball will also have a velocity to the right because of the conveyor belt's velocity in that direction. However, if I was on the conveyor belt with this person, let's say I am on this conveyor belt and this other guy is bouncing the ball up and down, up and down, up and down. I wouldn't notice the ball's velocity to the right because I'm alongside the conveyor belt with them. So the ball only has a velocity upwards of a certain value, not to the right, depending on, again, my frame of reference. Cool. Now let's move on to some key kinematics formulas, or basically, how does math tie into or tie position, velocity, and acceleration together? Well, first, let's look at the variables in which we use to symbolize position, velocity, and acceleration. I've used them previously in this, and yeah, that was sad. Okay, position is represented by the variable x. X is position. X with a little zero under it is your initial position. X with a F under it is your final position, or your position after a certain acceleration or a certain velocity, or you've undergone any change in your state. Cool. Now V is used to represent velocity. It has the um, same subscript of 0 and F to represent final and initial conditions. Acceleration is A, which is pretty intuitive. And while acceleration does not change in physics 1. So acceleration is always going to be a. It's not necessarily going to change unless you're undergoing circular motion or actually motion in a pendulum, which is not covered in physics 1. So you'll be a okay. Cool. So these are the variables, and these are different terms you need to know. So now let's look at how these are all the different formulas you need to know to have in your toolbox for the AP exam. Well, let's start with x, or your position at a certain point. Your position is equal to your change in velocity, or sorry, actually, if you think about position, it would only be expressed in terms of velocity. So for your position final is your initial position plus their velocity times how long you're traveling at that velocity. Your position is also equal to your initial position plus your, again, your initial velocity, not your velocity over time, because in this one we're implementing your acceleration, because in this equation you're traveling at a constant velocity, or your velocity is not changing and acceleration is not part of the equation. In this equation, you do have a changing velocity. That's why you add this 1/2 at squared at the end, which is calculus derived, and you learn about how we derive this equation in physics C. So this is your position if there's an acceleration. This is your position if you're traveling at a constant velocity. Now let's say you want to find your velocity at a certain point. Well, that is your initial velocity plus how much your velocity changed multiplied by the time you went undergo that acceleration. Your rate of change of your velocity is acceleration, which is a calculus topic, but I guess knowing that is helpful if you're in calc. Velocity, another equation used to represent velocity is change in position divided by change in time. Because as we know, the units for velocity are some change in position or some value to represent distance divided by some value to represent time or measure time. Cool. Now acceleration is equal to change in velocity divided by change in time. Same concept as velocity, where velocity is change in distance. Just like that, acceleration is change in velocity over a certain time. Now, just to like briefly cover, what is the difference between velocity and speed? So velocity is a vector quantity, or you have a velocity in a certain direction. So let's say I'm traveling at 15 meters per second. That has to be tied with a certain direction. I have to be traveling 15 meters per second in a certain direction. Let's say east, west, north, south, or a certain angle. Usually it's an angle in kinematics problems. Now, speed is a scalar quantity. Speed is just the magnitude of velocity, and that doesn't necessarily have to be tied with a certain direction. Well, you see how velocity is a straight line, right? When I represent velocity, I always use straight line. For speed, I could travel at 15 meters per second, like in a squiggly line or over a road. And this would be an accurate representation if I traveled at a speed of 15 meters per second. The direction does not matter in speed. However, the direction is key in velocity. Another formula that you should memorize is the change in your position, or how much your position changed, is equal to your final velocity squared minus your initial velocity squared over 2 times your total acceleration over that period. This is a little bit more of a complicated formula, but memorizing it is really helpful and can save a lot of time on your AP exam. Okay, now let's discuss gravity. Gravity is an acceleration which you feel on Earth. Earth is like a planet and it bends the space-time continuum. So let's say you're a guy on Earth. You are in this bend and it has a force on you or a force of attraction towards you, pulling you toward the center. Let's say you're a marble on this. You would roll inwards, which is how much you bend. Everyone bends space-time. Space-time is like a fabric and all objects bend it. However, how much it's bent, it varies from planet to planet. Your force of gravity is equal to, this is a different unit, but I'll just go over it. Um, the the constant of gravitation, which is a certain number, times your mass, times the mass of the object you're attracted to, divided by your distance squared, or radius squared. For Earth, your force of gravity varies, but your acceleration is always 9.8 meters per second squared on Earth. Now, let me give you an interesting question. Let's say I drop a feather and a ball, a heavy bowling ball, from the same height in a room with zero air resistance. Which object do you think will fall first? This may be unintuitive to what you've experienced in real life, but both of the objects will hit the ground at the same time. Why? Because their accelerations are the same. Remember our formula for distance traveled, or the amount of time that it takes? Well, we can solve for that. We can use our equation of delta x is equal to v initial t plus 1 half at squared. All I did was move the x initial to this side from this equation right here. I just moved this to the other side, and because of x final minus x initial is equal to delta x. And I got the change in position is equal to v initial t plus 1 half at squared. We can factor, um, we don't have a v initial because it starts off from rest over here at the top. So our change in position is equal to 1 half our acceleration, which is 9.8. It should be negative because we're moving downwards. So you don't really have to take a negative, but if it's moving, if you're starting off from a height and that's positive, and your height is going down over time, that means you're accelerating in the negative direction. So 1 half times 9.8 meters per second squared times t squared. Now we can solve for time by dividing both sides by 1 half times negative 9.8. And we get the t, and we square root both sides because there's a square on top of the t. So we get square root of the change in the height that is dropped from, or the change in x, divided by 4.9, or 1 half times 9.8, is equal to time. As you can see, the weight or the shape of the object is not taken into account in this formula. So both objects will take the same amount of time to travel a certain distance. This is key for various. This is a key concept to know for the AP, and they give you at least one MCQ about this. So yeah, look out. I hope you enjoyed this video, and see you in the next one. Bye.